Today, in this video, we are going to look into the relation between the electron configuration and the periodic table. To understand the relation between these two, first you have to learn how to do electron configuration of different elements using the periodic table. So before I start, let's do a quick recap on how to interpret the periodic table. So this is the modern periodic table. And as you already know, the periodic table has been divided into periods and groups. So there are 7 periods. Starting from the top, this is period 1. And remember, this yellow square which you see here, that is also part of period 1, then period 2, 3, 4, 5, 6 and 7. Similarly, it has also been divided into groups. There are 18 columns, 18 groups. Now, there are two different numbering systems, the traditional system and the IUPAC system. So, the traditional system has used the Roman numbers as well as the letter A and B. So, according to the traditional system, group 1 and group 2 is 1A, 1B. From group 3 to group 7, it is 3A to 7A. Group 8, 9, 10 is numbered as such. From group 13 to group 17, it's 1B to 7B. And the last column, the 18th group, is known as 0 group or the noble group. Now, IUPAC made it very simple. They just numbered it all the way from group 1 to group 18, from left to right. So as you can see it here, this is group 1 to 18. Now, in a lot of these periodic table images which you see, both the numbering systems are included. As you can see, the periodic table is color coded. Now, what exactly these colors stands for? Let's look into it. The first two groups which you see, which is in yellow greenish color, this is called the S block. And remember this little square on the top, that is also part of S block. Now let's look into, on the right hand side, there is a big square which is kind of orangish, brownish in color. These are known as the P block. In the middle, what you see here, the transition elements, this is called the D block. And the two rows at the bottom, the green ones, that's known as the F block. Okay, now let's look into the relation between electron configuration and the periodic table. And we will go one period at a time. So if we look at period 1, it has only S block. And how many electrons it can hold? 1 and 2. So S block can hold maximum of 2 electrons. Now let's look into period 2. Now period 2 has two different blocks. It has S block and it has P block. So how many electrons S block can hold? 1 and 2. That is 2 electrons. And after S block, which is the block you see? That is P block. And how many electrons P block can hold? 1, 2, 3, 4, 5, 6. So 6 electrons in P block and 2 electrons in S block in period 2. How about period 3? Period 3 is exactly the same as period 2. It has S block which holds 2 electrons and it has P block that holds 6 electrons. Let's move on to fourth block, fourth period. Fourth period is little different compared to first, second and third. Why? Because now you see they have 3 different blocks. Between S and P, they have D block, which is also known as transition element block. Now here, S block in fourth period will hold 2 electrons as usual. But before we go on to P block, we have to cross the D block. Now for D block, we have a little different rule. Why? Because it follows the Aufbau's principle. What is Aufbau's principle? That I will talk little later in the video. So the rule remains for D block is 4s, then it will be n minus 1. So when we come to D block, it will be 4s, 3d, and then again after crossing D block, it becomes 4p. Why that difference? Because as I said, they are the transition elements and they have variable valencies. So their two orbitals are unstable. So again I repeat, 4s, 3d, 4p. So for period 5, it will be 5s, 4d and 5p. For 6 and 7 period, the rules are again little different because there are 3 orbitals that are unstable, which you will learn about in the higher grades. Okay, now let's do electron configuration of a few elements. As an example, from period 1, we will be doing hydrogen and helium. From period 2, lithium and boron. From period 3, sodium. From period 4, scandium and gallium. So to do the electron configuration, we have to follow Aufbau's principle, as I mentioned earlier. So what is Aufbau's principle? It is basically distribution of electrons in the orbital. In other words, it is a guideline to fill the atomic orbital with electrons from lower energy level to higher energy level. And also, Aufbau's principle says that no matter what the atomic number is, how many electrons an atom have, we have to always start from the top. That is from period 1 and sub-level or block S. So we have to follow these arrows with me. So we have to start from period 1 to 1s to 2s, after 2s to 2p, then we move on to the next level, that is period 3. So period 3s, then it goes to p3, 4s and 4s to d. Now this d is the unique group where we have to follow a different rule, which is n minus 1. So after 4s it will be 3d, then 4p, 5s, 4d, 5p, 6s, and that's the way it continues. So keeping this Aufbau's principle in mind, let's do a couple of examples. First one is hydrogen. So where is hydrogen located? It's in period 1. It's the first member of periodic table and period 1. And what is the atomic number of hydrogen? That is 1. Atomic number 1 meaning 1 proton and 1 electron. So we are concerned here, we are focusing on the number of electrons.
Looking at the Aufbau's principle chart, we start from the top, that is from 1s. As hydrogen has only 1 electron, an s orbital can hold up to 2 electrons. So its configuration will be 1s1. Let's do the rest of the examples on the board.
Let's look into the next example, which is helium. Helium is also part of the first period, and the atomic number for helium is 2, and it's still helium is an s block element, as you know. So let's do the electron configuration for helium. So I'm going to write it down all over again. Helium has atomic number, that's 2. Okay, again looking at the Aufbau's principle, helium is still in period 1 with 2 electrons. Remember, we start from the very beginning. So we start from period 1. Helium is an s block element, so we write s. And how many electrons it has? 2 electrons. So we write 2. 1s2, this is the electron configuration for helium. So let's look into our next example, which is lithium. Now lithium, pay attention here. Lithium is in period 2. And how many electrons it has? 3. Why 3? Because the atomic number for lithium is 3. So it's in period 2, but still it's in block S, that is sublevel S. So let's do the configuration for lithium. So I'm going to write it again here. Lithium has atomic number 3, and we have to do the configuration for lithium. Now again, going back to Aufbau's principle, we always start from the very beginning, which is period 1 sublevel S. So period 1, which is sublevel S, can hold how much? 2 electrons. But lithium has 3, so there's 1 extra electron here. So what do? We move on to the next period, which is period 2, still in sub S level. And how many electrons left here? 2 already is in period 1, S2, and 1 extra, which will be 1. So 2 plus 1 is 3. So total number of electron here is 3, which is matching your atomic number. So this is the configuration for lithium. So the next one is boron. Boron still is in period 2, and the atomic number for boron is 5. So boron atomic number is 5. And if you do the configuration for this, we follow the same pattern, that is 1 S2, 2 S2, that is 4. What comes after? Period 2 has also p block in here. So when we have done 2 electrons in S block, still there is remaining electron. 2 plus 2 is 4. So how many extra electrons we have here? That is 1. So which will go in 2p, and that is 1. So 2 plus 2 plus 4 plus 1 is 5. And again that matches our atomic number. So electron configuration for boron will be 1s2, 2s2, 2p1. Let's look into our next example, which is sodium. Now as you can see, sodium falls in period 3, and the atomic number for sodium is 11. So how do we do the electron configuration for sodium? We follow the same steps as we did before. So again we write here, this is sodium with atomic number 11. And again we start from the top, so it will be 1s2, because S can hold maximum of 2 electrons. Then we move to the next period, which is 2s2. Now remember, in period 2, after S we have p block. So we have to fill the p block before we move on to the third. So it will be 2p6. So that is 6 plus 2 is 8 plus 2 is 10. Remaining electron is 1, which will go into the next period, which is period 3. Still the block remains the same. It's sub-level S. And how many electrons left? 1. So it will be 3s1. So the electron configuration for sodium will be 1s2, 2s2, 2p6, 3s1. If you add all these numbers, it comes the same as 11. Now let's take an example from a D block element. So let's do scandium. Now scandium has electron number 21, that is the atomic number 21. So how do we do that? We follow the same steps, right? That is, we start from the top and we continue after filling in all the orbitals. So let's do for scandium. Scandium is 21. So we start, as Aufbau's principle says, we start from 1s2, 2s2, 2p6, then we move on to 3s2, 3p6. Then we come to the next level, that is period 4. S block, 4s can hold 2 electrons, that is 2 electrons. But now the next one, how many electrons? Let's count. 2 and 2, 4, plus 6 is 10, plus 2, 12, plus 6, 18, plus 2 is 20. Plus 2 is 20, so still 1 extra electron remaining. Now remember what I said earlier for D block element, that there the rule is little different, where it is n minus 1. In other words, if it's 4s, then we have to minus 1, so it becomes 3d. So we write 3d and the remaining electron, that is 1. So this is the electron configuration for scandium with the atomic number of 21. Let's look into one last example. We will do gallium. Gallium has atomic number 31. It falls in period 4 and it's a p block element. So let's do the configuration. So I'm going to write it again. Gallium is 31, which is the atomic number. So again we start from the top, as Aufbau's principle says. So we start from 1s2, 2s2, 2p6, then we move on to 3s2, 3p6, then we move on to 4s, 4s2. Now after 4s, what comes? D block. And remember the rule, D for D block, it's n minus 1. So D becomes 3d10. If we count this, 2 and 2, 4, plus 6 is 10, plus 2, 12, plus 6 is 18, plus 2 is 20, plus 10 is 30. Still 1 remaining, which will go in the P block. So again, after 3D, it becomes 4p1. So that's the electron configuration for this element, gallium. Let's summarize today's session. So what we have learned today, that the periodic table gives us a lot of information. Number 1, it is divided into 7 periods from top to bottom. It is divided into 18 groups from left to right. Now the whole table is divided into 4 blocks. The first 2 groups falls under S block, which holds maximum of 2 electrons. The last 6 groups comes under P block, that holds maximum of 6 electrons. The middle portion, the transition elements, that is the D block, and D block holds maximum 10 electrons. And the bottom 2 rows which you see, that is the F block, holding maximum of 14 electrons. Now we also learned that there is a relation between the periodic table and the electron configuration. To do the electron configuration of the different elements, we follow Aufbau's principle. And according to Aufbau's principle, whatever we are doing, whichever electron configuration we are doing for whichever electron, according to Aufbau's principle, when we do the electron configuration for any element, we have always to start from the top, that is from period 1, block S. And we can move only to the next block after completing all the orbitals from that. Now I have an assignment for you. You have to write the electron configuration of these following elements, that is oxygen, aluminum, calcium, cobalt and arsenic.